Hey guys, my name is Adrian, and welcome to Organic Chemistry 1, Part 4 of these recorded sessions. Today we'll be going over, for most of y'all, Chapter 4, and in general, alkanes. So let's take a look at our agenda. Today we'll be going over alkanes and their properties, classification of carbons and hydrogens, nomenclature, Newman projections, chair conformations. So now we're getting to the fun stuff. A lot of these topics and material will be, carried over to the next few chapters and even OChem too. So this is where a lot of things get set up. So again, if you have any specific questions to these, or just want to, you know, go over certain topics, feel free to scroll around on and find them. I'll have the titles on each page that we do. Okay, so let's get started with alkanes. So first thing first, alkanes. You guys probably already know. You can have straight chains. You can have cyclic cyclic chains, things like that. So we know acyclic alkanes versus cycloalkanes have um, properties that make them special. So for cyclic alkanes, we can determine um, how many carbons, how many hydrogens. Same thing with cycloalkanes, right? So with acyclic, we know the formula goes like this: carbon with n number amount has hydrogens with 2n plus 2 of however many carbons it has as acyclic, right? And then same thing for cycloalkanes, it has its own formula, and you guys can probably already guess it has two less, right? And that makes sense. If it's closed up, it's gonna have two less hydrogens, right? Because it's the carbon is bonded with carbon instead of other hydrogens, right? So something like, let's see, four here, one, two, three, four there, right? We can count out the carbons. It'll have four carbons, but the hydrogen is going to be different because this one's closed, whereas this one's open, right? So it has an extra hydrogen out here, extra out here. This one, both of these are closed, so this is missing those hydrogens, right? So super simple. We don't really run into those kinds of things, like super simple things like this because as we'll know later on, you'll have more complicated structures, right? Obviously, but things like that. And then properties, we talked about properties, melting point, boiling points, things like that. Those apply with alkanes, right? So just a little recap. Stronger intermolecular forces equals higher boiling point and melting point, right? We know that. Hydrogen bonds are stronger than van der Waals, so obviously the ones with hydrogen bonds will have higher boiling points, melting points, right? Bigger surface area equals higher boiling point and melting point, right? And then for just specifically for melting point, more symmetry equals higher melting. And we know that more dense is harder to melt than something that's less dense, right? And then again, with solubility, alkanes, obviously they're what? Organic, so there's no heteroatoms, right? So soluble in organic. And you see here that the examples we drew, none of these are polar, right? So obviously insoluble in water, water. So easy as that. Again, with these properties, these apply to, we'll be going over alkenes and alkynes later on, so they'll apply to those as well. But good, good recap, right? Good recap. So now let's get on to practice questions with our alkane. And this is going to be quick because we already kind of did the boiling point and melting point. So let's see this one. Label the cycloalkane and the acyclic alkane. So let's see. So out of these, okay. So pause the video, take a second, and then this one as well. Label, label which molecule has the highest melting point and boiling point. So you guys know the drill, right? Okay, so take a second, pause the video, get back to me. Okay, so I'm feeling orange today. So let's see. Cycloalkane, we know they have the formula CnH2n, right? So which one does that relate to this? Right. So this one is a cyclic, right? And then our acyclic is CnH2n plus 2. So obviously this one would be acyclic. And these are just random ones, right? So these are neither. We can't tell, right? We can't tell. So that's what you should have gotten. So now for 2, we should have gone for the highest melting point. Which one do you guys get? Right. Because of the symmetry, right? Highest melting point. And let's see. For the highest boiling point, yeah, boiling point is also is this one, right? Because it's the surface area, right? So a little recap, not too crazy, right? Okay. So let me change the color and let's move on to our next topic, which is classification. So this comes in handy with just kind of even with hybridization, I guess, it kind of ties in, but it also makes things easier with just knowing where everything is, right? Because certain reactions attack certain classifications of carbons, of hydrogens, blah blah blah, right? And this is gonna tie into organic chemistry too when you start kind of pinpointing each and every carbon and hydrogen atoms. So, but it's not gonna be too crazy. You guys will get this like in an instant, right? Classification of carbons and hydrogen. So we have primary, secondary, tertiary, quaternary, right? So let's do carbons first. Carbon. So we have primary, secondary, tertiary, quaternary, right? So it'll look something like this. With primary, right? So, and let me label all these features. And we're looking at the middle carbon, right? And then you just keep adding carbons, right? Secondary, tertiary, quaternary, right? So simple. However many carbons you're attached to, that's what the carbon is, right? Um, okay. So what about hydrogens? Hydrogens is a little bit different, and this is actually hydrogens are important in classification because this will apply to like functional groups. So hydrogen classification is going to be the same as nitride or amide classification, things like that. So see this one, we're gonna have two, three. Okay, so this one we're looking at this hydrogen right? And then basically all of these are hydrogen. It's kind of like vice versa of the carbons, right? Right here, right? It's kind of vice versa. And you kind of notice there's no quaternary because if it's just all hydrogens, what's the point of classifying it, right? That's just gonna be um, all primary, right? So no quaternary because just taking a look at this picture, it doesn't make sense, right? H. That's just like one atom, one carbon, CH4. So that there's no classification for those. There's no quaternary hydrogen. So if anybody asks you if this molecule has any quaternary hydrogens, that's a no, right? That's a no. So that's for classifications, right? And this is important because again, you'll use this more in OChem too, but it sometimes naming will throw in a wrench in there saying, oh, what's the classification of this functional group? Primary, secondary, tertiary, things like that. And we'll see a little bit later how um, some reactions prefer primary over tertiary, blah, blah, blah. So we'll get into that a little bit later. Okay, so let's do practice. Carbon. So let's do this. CH2, CH3, CH3, CH3. Okay, so take a second to label all the carbons and hydrogens if they're primary, secondary, tertiary, quaternary, things like that. So pause the video and come back. Okay, so let's do, I guess let's do blue. So what did you get for this carbon? This carbon is your bond primary, right? Because it's only bonded to that one carbon. What about this carbon? Secondary, because now it's bonded to two. One over here, one over here. What about this carbon? Primary. This carbon? Primary. This one? Tertiary. This one? Quaternary, right? This one? Primary. Primary. Okay, so not too crazy, right? Now let's do hydrogens. Let's do green. This hydrogen, what did we get? Primary. This hydrogen, it has two carbons, right? Secondary. Um, this one, two, primary. This one, primary as well, right? Um, these two as well, primary, primary. Oh, what about this one? Tertiary, right? So, and that's it, right? And you notice here, there's no quaternary hydrogens, um, things like that. So not too crazy. If anything, this is just kind of like, having you in that mindset of like, okay, this molecule has all these moving parts or whatever, right? So, and these um, don't relate anything at all to hybridization, right? So these are all SVPs. So no correlation, no relation, right? Okay, so not too crazy, not too bad. It's whatever, right? So let's go on to the next one. Our next topic is nomenclature, which is huge, right? Okay, so nomenclature. First, with nomenclature, we have rules, of course, but just to kind of recap, we have parents and substituent chains, right? Like the methane, ethane, things like that. So parent chain. So one carbon all the way down to 10 carbons, right? Two, three, C, four, C. Oh, it doesn't fit, but okay, that's fine. So we have methane, ethane, propane, and you guys probably already know all of this. So if guys wanna fast forward, totally cool. Okay. We have what is four? Butane, pentane, so on and so forth. Hexane, um, heptane, octane, nonane, and 10 is decane, right? And then we have their substituents. If they're not the parent and they're just part of the structure, whatever, right? There's going to be methyl. Basically, you're going to replace ane with ill, right? Let me highlight that. So we have the anes to ills. So that's what happens when you become a substituent. And um, this applies to even when we're going to go over alkenes and alkanes, um, things like that. And it's a little bit different for like alcohols and the functional groups and things like that, but same concept. You replace the ending with an ill, right? So let's get back here. And then ethyl, propyl, butyl, pentyl. I mean, I'm pretty sure I don't need to write all this down, but I'm too deep into this, so I have to finish. I have to finish this. Heptyl, octyl, nonil, and pretty much mm, 5 to 9 you're not even gonna see because if it if it's a substituent that long, most likely it's gonna be part of the parent chain, and you'll see in a second when we start doing the rules and stuff, right? Okay, so that's that with the parent chains and the substituents and their substituents name, right? Now I need another page because I don't think it'll fit in here. Let's look at some special substituents, right? So we have 3 carbon alkyl groups, which as we know, 3 carbons are, right, propane, propyl, right, and 4C alkyl groups. Okay, so we have for 3, we already talked about it. Propyl is one of them, which is just one, two, three chains, right, bonded to something. So, and that means that's where it's bonded at, like it's bonded to something. But we have 3 here, one, two, three, and then isopropyl, which looks like which is a Y, right? So those are two, um, 3 carbon alkyl groups, and you'll see these a lot. Propyl, isopropyl, you'll see them a lot. And then for 4 carbons, same thing. We'll have butyl. We have isobutyl. We have sec butyl, and we have what is it? Tert butyl. So butyl one, two, three, four, right? Iso, and it's like a longer Y. One, two, three, four. Cut off here. Sec butyl. One, two, three. I drew this weird. Oh, this That's where it cuts off. So we have one, two, three, four. And then chip beetle is the chicken feet, right? One, two, three, four. So we'll see these a lot. Let's see. I'm gonna go over these with a colored one because I feel like it got confusing with the little wiggly line. So okay, so this is the propyl group, isopropyl, and the butyl, isobutyl, sec-butyl. Okay, right. So that's what we're gonna be looking for. If any of these are in a chain, sometimes, um, and we'll practice it, but sometimes just because they're in a in a structure, they're not always going to be the substituent, right? So they could be part of the parent chain, and so make sure to really follow the rules with nomenclature, and that's what we're going to go over right now. So the rules with nomenclature, and it's going to be the same. Um, this is going to be the base of every nomenclature that you'll find. You'll go over in OChem in general, right? But of course, once you get to more complicated structures, more complicated functional groups, you'll have exceptions, you'll have revisions, things like that. But we're always going to have parent name, right? And that's the longest chain, right? So if our longest chain was 10, then the ending, our parent chain is going to be a decane, something decane, right? Two, our suffix is going to be our substituents, right? Functional groups, things like that. Functional groups. Three, prefix equals the location of where those substituents are, like one butyl or um, like one isopropyl, things like that. Or I guess it doesn't make sense, but yeah. So identity, and this is also where once we start incorporating cis, trans, EZ, RNS, things like that. So pretty much everything that'll tell you where that functional group is. You're telling me there's this functional group where, right? And then amount, and that's where the die, tries, things like that come in. So okay, so how do we find it? We have find the longest chain, right? Easy, right? Continuous, it has to be continuous. Um, and basically, you just keep counting and comparing. See, if I go this way, is it going to be more than if I go this way, right? So, which one do you choose? If now there's a tiebreaker, if equal, if there's multiple ways that it can go up to 10 or whatever, if equal, choose one with most substituents and functional groups, right? So that's really important. Most substituents, and it makes sense because the whole point of nomenclature is to know what the structure is, right? So the more substituents you have, the more information you have of that molecule, right? The easier it is to name, the easier it is to identify, the easier it is to recreate, right? Two, numbering. So now you have the longest chain, now you number it. Number with regards to closest substituent. So again, with the substituents, right? Closest substituents. So that's important also because a lot of people choose the wrong way. Like they have the parent chain and everything, but they choose to number it like backwards or another way that makes the closest substituent um, in five instead of getting it to two, right? So things like that. Now, if there's a tie, like if you go this way, this one is two, but if you go this way, this one's two as well. If tie is equal, choose alphabetically. Choose alphabetically. Yeah, I should have room. So now, and then three, combine the substituents, right? So name the substituents, combine, name, and combine alphabetically. Alphabetically, right? So, and that's all, right? And alphabetically, we don't count sec or tert like with the butyls and stuff, but we do count iso. Um, not sec or tert. So we don't count sec and tert when we're doing alphabetically. So if we have a sec butyl, we'll count the B instead of the S, right? So, and also if we have with the amount, right, over here, amount, like the di, tri, etc. If we have more than one substituent of something, we'll have to use di, tri, however many, right? Okay, I feel like this is better if when we have examples. So let's get on with the examples. Let's do this. You guys should have told me earlier. So, okay, I'm gonna give you a couple, and then we'll name them afterwards. Okay? This surface is so smooth. Um, so I'm blaming it for the bad drawings, but I think I just have bad handwriting in general. Let's see. And I tried to pick like the best examples for these, so we can kind of like see all the different things that we talked about. So, you know, and I don't think we talked about cyclic, but we did say naming is the same for pretty much most things, and we should be able to name this. Okay, so take a second, pause the video, get back to me with names. Okay, so you guys got the names. This is what I got. So let's see. 3 methyl, 2,5 tri methyl, 4 propyl, um, heptane. And let me give you guys the name for all of these um, before we discuss. And let me do different colors because I feel like this is gonna overlap. 5 sec butyl, 3 ethyl, 2 7 dimethyl decane. Ooh, okay, that was rough. Sorry. Okay, and this one. This one, if you didn't get it, I'll give you a pass because we didn't really talk about it, but you'll see how it's like just the same. It's same old, same old. Isopropyl to methyl cyclohexane, right? And we didn't talk about it, but it's a good surprise, right? It's a good surprise. One cyclo pentyl hexane. And you guys are all wondering what? Okay, so let's go backwards because I'm already in yellow. So, what do you notice between these two? We have a chain, we have a cyclic. So, between these, we can't count like this. We can't count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can't do that, right? It's either the chain or the ring. So, to prioritize that, what's the number one rule? Find the longest chain. Which one has the longer chain? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Oops, I'm sorry. I cut out a thing. Ooh, there. Sorry about that. Ooh, I sounded British there. Okay, sorry about that. Okay, so as I was saying, we find the longest chain, and if there's a cyclic, we either go with the cyclic, or if there's a chain, we go with the chain. So whichever one is the biggest one, is the longest chain, continuous chain. So we have here 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5. So which one more prioritized? The one with the six, right? Okay. So now I always circle my substituents. So I'm gonna circle this because now this is a substituent, right? So now we said our second one number with the substituents at the lowest number, right? So if we number from here, 1, 2, 3, 4, 5, 6, our substituent, the one I circled, would be 6. But if I number from here, it'll be 1. So it only makes sense if we number from here, right? 2, 3, 4, 5, 6. And we know this is a cyclopentyl, which is what we have here, right? And that's why we have 1. And we're indicating where that cyclopentyl is, right? Because it's not on the second carbon, not on the third, not on the fourth. It's on the first carbon. So 1 cyclopentyl, and then our longest chain, hexane, right? Easy as that. So let's do it with the second one, where I didn't mess up the drawing. I don't think. Right? So now we know to find the longest chain, and obviously this one's the longest chain with 6, right? So now our dilemma is, who do we number first? Because we can start here with 1, we can start here with 1, we can start here with 1. So now there's three-way tie. What did we say when there was a tie? We go by alphabet, right? So this one is a sec-butyl, this one's a methyl, and this one's iso propyl. So which one's alphabet? Um, which one is our priority? The sec-butyl, right? Because when we're doing alphabet, we don't care about the sec. We go straight to the butyl. So this is B. So we'll number here 1. And why did we go to up here and not down here? Good, because we went up because that's our second lowest substituent, right? And if we go down here, we would have gone 2, 3, 4, 1, 4 instead, and that's um, obviously there's gonna be a higher number than 2 and 4, right? So 1, 2, 3, 4. So that's why we numbered it the way we did, right? So nothing too crazy. Um, just follow those rules and you'll be fine. And this applies to everything else. And again, with applying to everything else, just imagine these functional groups of like alcohols or halogens. Same rules, right? Okay, so this one we should have numbered the longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Then our substituents, methyl, ethyl, butyl, methyl, right? And this is where I was talking about with we have two methyl groups, right? So we indicated where those both are, and we said dimethyl, right? And a lot of people forget that, di. And this is easier, especially when you have multiple choice, because you can kind of check off every single thing. But some classes are not multiple choice, so you're gonna have to find them on your own, right? And knowing that on your own automatically, right? But with practice, I'm pretty sure by now you guys got it. But let's do this last one. Again, longest chain, and we're numbered from here to oops, 4, 5, 6, 7. Our substituents 1, 2, right? And again, here we have like three methyls, right? Right. Trimethyl. And actually, I forgot a number. Yeah, there should have been two. Ooh, what a mess. 235 trimethyl. Okay, so don't be like me. Don't forget that. Don't forget that. I don't know how I forgot that with the trimethyl and just having two. But yeah, you guys get the point, right? Sorry for all the mistakes, but you guys got it. You guys got it. You guys are good. Okay, so now let's move on to our next topic, which is human projections. And these are fun too. So you guys don't really use them a lot except for like in this chapter. So, but they're still pretty cool. You know, um, they look complicated, but not really. Once you start getting a hang of it, right? Human projections. For a second there, I thought I was saying new human, but it's human projections, and they come in two forms. We have eclipsed versus staggered, and you'll see why in a second. And staggered has subcategories with let's put here anti-gauche, right? So with these, pretty much the purpose of Newman projections is that they are different arrangements through rotations. So we know we kind of talked about this a little bit in the last video how we talked about double bonds can't rotate, but single bonds do. So we're talking about single bonds, obviously, so they can rotate, right? So now we're kind of putting that into practice. Newman projections, they rotate. So through rotations in single bonds, and with that, there's also strings, right? We're gonna come across. Um, Actually, before that, Newman projections, I guess the basic or the base of the drawing, you're gonna see something like this, right? This one indicates the front carbon, right? So since we're rotating it, there's going to be a front carbon, and then this is the back carbon. And it's this is probably one of the harder things to visualize in this in OChem 1 because it's just weird, especially when you get into bigger molecules. And trust me, you will see like bigger ones and they go crazy. But think of it as um, this is the front carbon and this is the back carbon, right? So this back carbon can be bonded to like three other things, right? So it's bonded to this one, and it can be bonded to three other things. And it says different arrangements through rotation. So this could be up here, this could be to the side, whatever, right? So this they're kind of rotating, right? So that's what that means. So we'll talk about that a little bit more later. Once we start getting examples, it'll make much more sense. Okay, so now because of that, we have torsional and strains. We have strains because this could have something bonded. This could have stuff bonded to it, right? And this one could have stuff bonded to it. So now they could collide, right? They could get too close or whatever. So there's strain. We have torsional strain, and we have steric. And steric strain we'll hear a lot, especially once we start getting into reactions as well. Because if you're strained, you're not gonna react with something, or if you're too, you know, they prefer it's faster or whatever. Some molecules are too big to go through a strained molecule than an opened one, right? So things like that. So steric strain increase in energy when non-bonded atoms are too close. So, like I said, right, this carbon could have bonded stuff to it too, and this carbon could have bonded stuff to it too, and these could be too close, right? Torsional, I don't know why I started with steric, but torsional, um, increase in energy caused by eclipsing. So, eclipse, caused by eclipse. So, same, um, same concept, but this time it's when they're actually eclipsing, and you notice that that's one of our projections, right? So, and then also just for kind of setting this, you know, further down the rotation and strains and all that, variable to rotation, a more straightforward thing, right? So obviously there's going to be something inhibiting the rotation that we talked about, right? So energy difference between the lowest and highest energy, energy conformation. And again, that deals with steric strain and well, all the strains really. That deals with all the strains because we know if it's strain, it's unstable. If it's unstable, it's what? High or low in energy. High energy, right? So things like that. Stability, um, all that. And we'll talk about that later. Actually, no, we'll talk about now because examples. It's example time. Okay, so let's see. That was a lot of writing, and all of those are good concept questions. So, or vocabulary words, I guess. So, keep that in mind because all those things are pretty much the same thing but different definitions, right? So, okay. So first, let's do label. Mm, if they're clips, um, staggered, and I'm giving you discussion um, because you guys already know what these are, right? You guys should already know what these are or have gone over it. So this is just reinforcing it. So again, you know, this isn't a substitute for lecture. So definitely go to your lectures, um, and you know, do all that good stuff. Okay, staggered, and if it's staggered, gauche or anti, right? And then, since I already know that you guys already went over this, and which one is the and the highest and lowest energy. So which one has the highest and lowest energy? So let's see. Let me set this up so I have room here. Lots of H's. These are probably the worst drawings you could have ever seen, but it's okay. It's about the concept that counts, right? It's about the concept that we'll be learning afterwards. That'll really hit it home. So, and you kind of see how I'm kind of just rotating this. Okay, so pause the video, take a minute, and label as I guess label as many things as you can about these. Tell me as much as possible about these four molecules, these four projections. Okay. Okay. So eclipse, staggered. Let's do let's do the eclipse and staggered stuff first. Let's do energy later. So this one you should have gotten staggered. And what kind of staggered is it? Anti, right? Because of that 180 separation. Anti is 180 apart. And yeah. And with that, it's we know. Oh, let me color code this to kind of make more sense. So we know the pink is the front carbon, right? And let's do the blue is the back carbon. And the way to tell if it's anti-ghost, things like that, we look at the priorities of each of those carbons. So what's the priority in the front carbon? What's the priority in the back carbon? So the priority is just like with the R and S, which one's the biggest molecule? Because we talked about the strains, right? So obviously the bigger the molecule, the more strain it will contribute or affect the whole molecule. So that's what we're looking for. We're looking for on the front carbon, which one is the biggest? On the back carbon, which one's the biggest, right? So on the front carbon here, and I'll go back to pink. Well, I'm not even gonna circle them because on the front there's a CH3, on the back there's a CH3. All of them are the CH3, so we're comparing the CH3s obviously, but it can be bigger molecules, right? So that's what we're looking at. We're looking at the CH3s. We're comparing those priority groups and determining um, staggered and anti, right? And this one, staggered and eclipsed, right? Oh, sorry. Ooh, ugly. That's ugly. Okay. Staggered and gauche, I should say. Ooh, I think I just made that really bad. Okay, that's really bad. Okay. Maybe you guys can probably fast forward to when I have this done. Okay. Let's see. This is too funny. Okay. That's good enough. That's good enough. You guys can tell. Gauche. Staggered gauche. Same thing over here. Staggered and gauche. And gauche, so we said anti was 180 apart. Gauche is 60 apart, 60 degrees apart. And you can kind of see these are 60 degrees, and you can kind of just tell by the angle between these bonds, right? So 60 degrees. And this one's eclipsed. An eclipse is 0 degrees. It's just front to back, right? Front to back. So think of it eclipsed, gauche, um, eclipse, gauche, um, just regular staggered because they're not 60 degrees apart anymore. Just staggered anti. Right? Oh gosh. Okay. So I don't have models. I just have hands. Okay. So now we have this, and now that we have this, it's going to be super easy to see which one has the highest and lowest energy because all you need to know is that anti has the lowest energy And what did we say about lowest energy? More stable. And then eclipsed, highest energy. So that's that, right? So highest energy, so more unstable, unstable, stable. Ooh, that's it. That's it with Newton projection. Okay. So now the harder thing with Newton projections, and we'll go to another question here, is to kind of how to say this, to kind of see it from skeletal and turn into Newman and vice versa and all that, right? So I'm gonna give you this little question over here. Newman projections, and let's see. Um, convert this, convert into Newman projection. Looking, looking down 3 to 4 carbon in the most. So draw these two different ways. In the most and least stable. So, and this is okay. So, give you guys a couple minutes. Pause the video. Draw me the most and least stable conformation looking down 3 to 4 carbon. Okay. So, you guys. Oh, let me do another color. Just that blends in. Okay. So, first of all, we have to find out which is the 3 carbon and the 4 carbon. And this is going back to nomenclature. And you guys should have gotten this, right? That's what you should have gotten. So it says we're looking down 3 to 4 carbon. So we're looking down this way, right? And um, you know, you guys have probably seen this in class, the eye. We're looking down this way. So now we just convert that into Newman projection. So we have, let's see, let me draw. So Newman projection, we always start with the carbon in the front and the carbon in the back. So obviously this carbon in the front is the 3, right? And this carbon in the back is the 4. And actually, I'm gonna even give you guys more colors to kind of visualize this. This carbon has um, this methyl group here, and it has 2 hydrogens, right? And this one has 1 hydrogen. So let's do the back first. So let's do the 4th carbon, and we're doing it let's do the most stable. So it has 2 hydrogens, right? And then we said the priority group, which is the 5th carbon here. So now let's do the um, the next one, the 3. It has 1 hydrogen, right? And then it has a methyl group, which is this one, right? And then what's this? What group is this? 1, 2, 3. Isopropyl group, right? Yeah, that's an isopropyl, right? So that's how you do that. Hopefully that you guys solved that. And obviously this one's the most stable because it's anti, right? Most stable anti, and we see that the priority for the back is just the methyl. So we're comparing the methyl against the isopropyl here in the front, right? And pretty much since we got this, we can just rotate it into the most unstable, which is, or the least stable, I guess, which is the, what's it called? the eclipse, right? So again, let's start with the two dots, and then we'll do the same thing. Let me keep these here. H, and then, oops, no, wrong one. So let's cover this up. Thank God for this black one. Honestly, this isn't an eraser. This is just the black, the black pencil. So, okay. And then we said it has the methyl group up here for the back. And so now we're rotating the front carbon to make it eclipse, right? So this front carbon now, and I'm gonna do it a little bit curved so you guys can see everything. So now it's gonna be right behind that isopropyl group, and then wherever we put that methyl group is wherever, right? And then we'll have that one hydrogen, right? So this is this looks really no, it doesn't look terrible. Yeah, it looks good. So least stable because it's the eclipse, right? So this can go a lot of different ways when getting asked a question. Draw this, convert this to that. You can even go from human to skeletal, right? So you can do vice versa. You could get asked most stable, least stable. Same thing as getting asked highest to lowest energy, right? So play around with that. It's pretty fun once you get used to it. And if you get given bigger molecules, it's the same concept, the same format, the same steps that we took. And you can kind of see the colors here. Use colors in whatever you're doing. So fun, fun. So now let's move to our last topic. Um, and this one's fun too. Chair confirmations. You guys probably think I'm crazy laughing at all these fun OChem things. Honestly, I don't know. I'm probably just losing my mind. Oh God. Okay. So chair confirmations. So first thing that we want to talk about with chair confirmations is why they happen, why they turn into chairs, right? That's probably what you're thinking. And that's because of, again, more strain, angle strain, right? And this is when um, you get angle strain when bond angle deviates from 109.5 degrees. So we know 109.5 degrees is sp3, right? So if it's not sp3, then there's an angle strain. And sometimes angle strain's too much, especially I guess let me add this for cyclic okay, for cyclic. So sometimes it's too much, especially for cyclic molecules that they have to kind of like pop up, right? To kind of like um, maintain that 109.5 degrees. So they kind of like bend, twist, acrobatics, all the acrobatics, right? So um, it eliminates chair confirmations, eliminate eliminate angle, and from earlier, torsional strain. So that's the goal of chairs. That's the goal of chairs. Okay. So, and this is the word they're gonna use is puckered. Okay, puckered. So with chair confirmations comes new terms, new terminology, new kind of what's called descriptions, I guess. That's a good word. Descriptions. So we have axial and equatorial. So axial is perpendicular to the plane, to plane, and equatorial is the equator, right? Equator. So with these, that's just that, you know, axial, straight up or down, right? Straight up, straight down. Equatorial, side, right? So side to side, whatever. And we know with chair conformations, they can um, flip, right? They can flip. Next thing you know, they're here. Next thing you know, they're there. So, and I'm gonna color this because this is really, really important. And I'm gonna do it here. So when ring flips, um, direction same, and then position flip, flip. So if it's okay, it was kind of a bad idea putting it there, but it's a different color. So um, I'm just gonna start so you guys don't think I like cross it out. But when it flips, the direction stays the same. So if it's up or down, it's still gonna be up or down, and then but the position is gonna be flipped. So if it was axial up, now it's gonna be equatorial up, right? That's all that means, and but it's really important. Um, so let's see, and more about check confirmations. Let me go to a new page. Check confirmations. That you're gonna have another type of strain, which is the 1-3 diaxial interaction equals unstable, unstable. So just like the word, the name says, 1-3 diaxial. So two axial substituents, right? Which makes sense. And then also with stereoisomers, just to mention it, isomers, there's gonna be cis and trans, which we already know. Cis is gonna be um, kind of the same as this diaxial. They're gonna be um, not stable, right? Cis versus trans. So just keep that in mind. Obviously, if one is up and one is down, that's trans. If both are up, that's cis. That's all it's saying. I just wanted to mention that. Okay, so let's see. Let's do practice, and you guys will probably find that much more helpful. Practice, 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 right? Honestly, drawing these is probably harder than understanding them. Okay, so let's have which one is um, trans 1,4 dimethyl cyclohexane, hexane, right? And the most stable. So let me draw these. I'm gonna try my best. This is one take. Okay, nailed it. Ooh, nailed it. Okay, this was the best one, I think. Okay, so and let me give you yeah, let me give you another one, and then you guys can do that. Draw the most stable conformer of this. Okay, so take a second, pause the video, and tell me what you got. Okay, so you're back, and I forgot to tell you that equatorial is stable, axial, less stable. So keep that in mind. Equatorial is always going to be more stable than axial, no matter what. No matter what. Okay? And that's kind of like cis and trans. Trans is always going to be more stable than cis, right? So, okay. So what did you guys get for the first one? You guys, I got, let's see, what does it say? Trans. So, right away we should have up and down, right? So this is up, down, up, down, 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 down. So obviously this one's the only one that's trans, and actually the most stable as well because it's the only trans one. So automatically it's more stable than cis, right? So this is also most stable, right? And 1,4-dimethylcyclohexane, 1, 2, 3, 4. They're four apart, right? 1, 2, 3, 4. This one is 1, 2, 3. This is 1, 3. Um, this is cis 1, 3 actually. So we can even name that. We can let's name it for fun, right? So this would be cis 1, 3, whatever, right? And what about this one? 1, 2, 3, 4. This one's cis 1, 4 dimethylcyclohexane. So none of those are it. And these are, and actually here, good thing I caught this because I don't think I have a question like this. But this one is diaxial strain, right? Because it's 1, 3, and they're both axial. Diaxial strain. Good thing I caught it. Okay, so diaxial strain. So this is actually the least stable. So least stable, least stable. So there you go. And obviously these are equatorial, and this is what they look like. They're not like straight, to the side. Um, they look like this. They're just bent. They're equatorial. So equatorial, and actually you can even just look at this has one axial, one equatorial. This has two equatorials. So obviously the one with the more equatorials, the more stable. Okay, equatorial. Okay, so now let's go to the second one. Which one of these um, draw the stable conformer? So what I always do, I start with a chair. So basic chair, whatever, right? So now we know that the most stable is always going to be equatorial. So obviously we'll be doing two equatorials because that's the most stable conformer. And now let's go back over here. Let's number it. One, two, three. So they're three apart, right? One, two, three apart. So we can just do, and since we're doing what? These are also cis, right? Cis. So we should draw cis equatorial something, right? So we can start from wherever point we want to. I always start at the tip. Most everyone does. Um, so let's do equatorial down OH, and then another equatorial down OH because that's we're cis, right? So they're both down, and there's 1, 3 apart. 1, 2, 3. So that's all it is, right? If we wanted the least stable, let's do the least stable. Let's do red. So this is going to be the most stable, and the least stable would just be same process. Let's do generic chair, but now it's this, and we want the least stable, and we know least stable is axial. 1 and then 3, right? OH, OH, and you see how there's that diaxial strain. Diaxial strain. So we don't want that. So this is the um least stable. Okay, hopefully you guys are following along because that's got crazy. The red is pops. The red pops. And it's kind of bright. But okay, so that's that. I have one more for y'all. And I think this one, okay, this one we're going to be flipping. So flip that chair, right? And you'll see how it's super easy how it's going to be, it's the same concept, it's the same process, especially from the second one, that's probably going to be the exact same. So, okay, so let's do this one. So HO again, it's popular. And let's do CL here, CL over here. So flip it. Take a second. You know, um, pause the video and come back to me. Okay. So again, generic chair. Let's do this one. So actually, this one, oh, I didn't tell you guys. Sorry. Um, we're gonna do. Oh, I should have told you guys what to do. Sorry about that. So okay, come back. So draw, draw most stable conformation and flip. Okay. Oh, that got a little aggressive. So now pause the video and come back once you got your flip. So again, generic. Ooh, that's the best one so far. Yes. So now let's number them. And this, I'm just we're not numbering it to name it or anything. So it's just like where everything is, blah blah blah. So 1, 2, 3, 4. So that's where everything is. And you see how these two are the same and this one's different. So as long as there's two cis and then one that's opposite of whatever they are, you're good. So let's start with HO first. And since we're looking for the most stable, again, all of these are going to be equatorial, right? So let's do OH over here, equatorial down. So since we did this down, both of these should be up. So the 2 would be up here. Oh, that's axial. My bad. Look at me messing it up. Okay, look at me messing it up. I almost messed up that perfectly good drawing. Okay, so let's put it here. Let's do CL here. So equatorial up, right? And then on the fourth one, and it has to be the same as this other CL, also equatorial up, right? Boom. We have two ups, one down. So that's what we have, right? And it doesn't matter if it's dash, if dash is up or down, as long as it's the same as this other CL and different from this OH, right? Whatever. So now we flip it, and we said um, position same, or I mean direction is same. Position is flipped. Come on, Adrienne, get it together. Okay, that's fine. Fine. We got plenty of time. You guys can always fast forward through all my mistakes, through all my erasing. Okay, it's to keep you guys awake, honestly. Position flip, direction same. So again, when we flip it, let's do it a different blue. Okay, so obviously this is going to be flipped, right? So it's going to be backwards like that. So now our OH, let's actually number this. The same thing we numbered over here with our OH over here. So 1, 2, 4. So now our 1 is over here, our 2 is over here, our 3 is over here, our 4 is over here, right? So that's how you should be looking at it. So now let's put where everything is. So this one is OH. It's still going to be down, but now it's axial, right? Because the position flips. This one's going to be up, but now it's axial. This one's going to be up, but now it's axial, right? And you kind of see how the most stable turned into the least stable. All these are axial. All it has steric strain, right? So that's all you have to do. So you can kind of see how obviously which one will it prefer? The most stable one, right? Most stable, and it flipped to the least stable, which makes sense because all the equatorials turn into axial. So um, that's obviously gonna happen, right? Okay. And by the way, this is how you flip it, right? You just pretty much the little flaps here um, just go up and down. Think of it as like the origami type thing, right? Just you can fold it up, you can fold it down. That's how you kind of see this. Um, thing like that. Okay, so that's all I have for you guys today. Again, we went over these topics, these amazing topics. They're great. And hopefully, you guys will join me next time for the next one. So hopefully that helped, and I'll see you guys later.